Alright, we'll be looking at the weight of objects in space. Weight of objects in space. It says when an object is on or near the surface of the earth, it experiences the full extent of the force of gravity or acceleration due to gravity of the earth. However, if the object, for example a satellite, is launched into outer space at a distance from the surface or center of the earth, the weight of the object reduces because the earth's gravitational force on the weight diminishes in proportion to its distance from the earth. The farther the distance from the earth, the lesser the weight. So the farther the distance of that object from the earth, the lesser the weight. So it shows us that the farther the distance of an object from the center of the earth, the lesser its weight. That means the weight of the object reduces in space. Okay, so this is it. It says, however, if the object, for example a satellite, is launched into outer space at a distance from the surface or center of the earth, the weight of the object reduces because the earth's gravitational force on the weight diminishes in proportion to its distance from the earth. So as it goes into space, you find out that the object's weight reduces because of the gravitational force on the earth, in proportion to its distance also reduces as well. Okay, so take note of that. Now we are going to solve a question still on the weight of objects in space. Take note that when an object has been launched into space, its weight reduces. Here it says that the farther the distance of that object from the earth, the lesser its weight. Okay, so we have a question on the board. The question says if the weight of a satellite on the earth's surface is 2000 Newton, what would be its weight when it is, Roman figure 1, at a distance equal to the radius of the earth from the surface of the earth? Roman figure 2, at a distance of 1.28 times 10 raised to power 7 meters from the surface of the earth. Roman figure 3, at a distance equal to 4 times the radius, capital R, of the earth from the center of the earth. And B says, for each case in A above, derive an expression for the acceleration due to gravity, gs, in space, with respect to the acceleration due to gravity, ge, on the earth. Then we are told that the radius of the earth is 6.4 times 10 raised to power 6 meters. Okay, so take note. Let's solve this question quickly. Okay, so we come back to that question. And it says the weight of a satellite on the earth's surface is 2000 Newton. So you take note of that. First, you say that the weight of the satellite on earth, represent it as WE, which is 2000 Newton. Okay, continue. It says what would be its weight when it is at a distance equal to the radius of the earth. Now we also take note that the weight of satellite in space, is WS. It is unknown for now. Then we also take note that the mass of the earth, in this case, is capital M. Of course, we know most times we represent the mass of the earth as ME or M subscript E, but here we are taking it as capital M. Then we say the mass of the object in space is small m. So the mass of the object on earth is capital M, while the mass of the object in space is small m. Okay, so take note of that. And then the radius says that the radius of the earth is capital R and is equal to 6.4 times 10 raised to power 6 meter. Also, we also take note that the the acceleration due to gravity, acceleration due to gravity on Earth is ge, and acceleration due to gravity in space is gs. Okay, so take note of all this. Acceleration to gravity on the Earth is ge, acceleration to gravity or in space is gs, and then the radius of the Earth is capital R. Okay, so take note of that. So we'll come back again to the question. It says, what would be the weight of that object when it is at a distance equal to the radius of the Earth from the surface of the Earth? A distance equal to the radius of the Earth from the surface of the Earth. So take notes. We are looking at A, draw figure 1. They say the satellite is at a distance equal to radius of Earth from surface of the Earth. Okay, so satellite is at a distance equal to the radius of the Earth from the surface of the Earth. So if we take this as the Earth, and then say this is the Earth, and then this is our satellite, that's the Earth, and this one over here is the satellite. This is the center of the Earth. This center of the Earth, that means the radius of the Earth now will be capital R from this center. And however, we are told that the satellite is at a distance equal to the radius of the Earth from the surface of the Earth. Now, this point is called the center. This point is called the center of the Earth. Okay? While over here, you call it the surface. Okay, call it the surface of the Earth. So this movement is from the surface of the Earth. The distance of that satellite is from the surface of the Earth. Or rather, okay, so distance between the satellite and the Earth is actually from its surface. And we are told that they say the satellite is at a distance equal to the radius of the Earth from the surface of the Earth. So from the surface of the Earth to this point where the satellite is, its distance is r. Okay, take note that is at a distance equal to the radius of Earth. That distance is what? Is r. Distance of the satellite from the surface of the Earth is what? R, which is the radius of the Earth. Okay, so take note, it's at a distance equal to the radius of the Earth. So we have this, that is capital R. Now the next thing we'll look at here, using Newton's law of universal gravitation. We're having that F is equals to G M1 M2 over R square, using Newton's law of universal gravitation. So it then means that what we made use of here is Newton's law of universal gravitation. You see Newton's law, Newton's law of universal gravitation. So it means that if F is equals to G M1 M2 over R square, remember what we are looking for is the weight of the satellite in space. So that means F changes to what? WS. Okay, so my F will change to WS, and then my M1 changes to capital M, which is the mass of the Earth, and my M2 changes to small m. Okay, so that is the mass of the Earth, or mass of the object on Earth's surface, and then the mass of the object in space. And this is the weight of the satellite in space. Okay, as that object in space. Alright, and then r, small r, changes to the radius of the Earth. That is capital R. And then what will I be having? That formula now changes to, you have that W, we are having W we're having W S will be equals to G capital M small m over, my distance now will be, you have to add these two, because it is the distance from the satellite from the center of the earth, distance of this satellite from the center of the earth. So you add them, as arrow plus arrow, and I'll be having arrow plus arrow all raised to power of 2. Okay, so then implies that WS will be equals to G M small m over 2 arrow raised to power of 2. Okay, and 2 raised to power 2 is 4. Arrow raised to power 2 is arrow square. So I'll be having WS equals to G capital M small m over 4 arrow square. Okay, now if I separate them, I then have that WS, which is the weight of the object in space, or weight of the satellite in space, is equal to 1 over 4, or you can say M over 4 rather, times G capital M over arrow square. Okay, if you observe this now, you observe that this is similar. See, this is similar. You observe and you see that this is similar. You observe and you see that this is actually similar to what's it called? See, but GM, but small g is equals to GM over arrow square. Yes, this is actually similar to acceleration to gravity on the earth, which is capital G ME over what? RE square. Okay, that is it. That's the acceleration to gravity on the earth surface is the gravitational potential times the mass of the earth over the radius of the earth. So it is similar to this. Okay, so that means that in place of this GM or capital R square, I will replace it with what? Small g, and then the weight of the satellite in space will be equals to M over 4 multiplied by small g. Now we're having that WS is equals to mg over 4. Okay, so mg over 4, and that mg there shows you that mg is what? Is weight, isn't it? So this means that WS will be equals to the weight of the satellite on Earth over 4. Why? Because WE is what? mg. That is the weight of the object on Earth is the mass of the object times acceleration into gravity. Okay, so that is it. And the weight of the object on Earth was 2,000. So that means that WS will be equal to 2,000 divided by 4. If you can recall vividly, I told you that WE, let's come back to that the weight of satellite on Earth, WE, is 2,000 Newton. So that means that I will replace this weight of satellite on Earth with 2,000, and I'll have something like this over here, as the weight of the satellite on Earth is 2,000. WS will be equal to 2,000 over 4, and if I divide that, that gives me 500 Newton. So you see that the weight of the satellite is 500. The weight of the satellite in space is 500 Newton. Okay. All right. So we'll look at the next case. It says the satellite is at a distance of 1.28 times 10 raised to power 7 meters from the surface of the Earth. Now, if you look at this, we are told that it says recall that the radius of the Earth is 6.4 times 10 raised to power 6 meters. Okay. Now, if we then check this, look at 2 times 6.4 times 10 raised to power 6 meters. It gives you 1.28 times 10 raised to power 7 meters. That is, using your calculator, your scientific calculator, you have that 2 times 6.4 times 10 raised to power 6 meters. We give you 1.28 times 10 raised to power 7. It then means that it says, therefore, the satellite is at a distance equal to 2 arrow from the surface of the Earth. Okay, since 2 times this gave us 1.28 times 10^7, so that statement then means that the satellite is at a distance equal to 2 arrow from the surface of the earth, because 1.2 times 10^7 is 2 times 6.4 times 10^6. That is 2 arrow, which is 2 times the radius of the earth. Okay, so I'll first draw my earth. I'll draw the earth, the diagram of the earth there. So this is the earth. That is the diagram of the earth. Then I draw the satellite. Draw the satellite over here. And then this is the center of the earth. And the radius of the earth from its center is capital R. Okay. However, we are told that the satellite is at a distance equal to 2 arrow from the surface of the earth, and this is the surface. That's the surface of the earth. At the circumference, you take it from the surface of the earth there to the satellite, and that will be 2 arrow. So the satellite is at a distance 2 arrow from the surface, that is at the circumference of the earth. You take it. Okay. That means that the weight of the satellite in space, will be Ws, using Newton's law of universal gravitation, is G, mass of the earth, times the mass of the satellite in space, over my distance now will be arrow plus 2 arrow. That is arrow plus 2 arrow, all raised to the power of 2. Okay, arrow plus 2 arrow, all raised to the power 2. And then I'll be having Ws equals to G capital M small m over arrow plus 2 arrow gives you 3 arrow. 3 arrow all raised to the power of 2. If I square that, I'm having that Ws is equals to G capital M small m over 3 raised to the power 2 is 9. That is 9 arrow square. Arrow raised to the power 2 is arrow square. So I'm having this G capital M small m, and you know that capital G M is the mass of the earth, and this is the mass of the satellite in space. Okay, and then if I separate them now, I will have that Ws is equals to M over 9 times capital G capital M over arrow square. Okay, so I'm having something like this. That is the weight of the satellite there. The space becomes this, gotten from that formula. Alright, so I'm having something like this. And also recall that capital GM over capital arrow square is small g. Okay, remember it says but small g is equals to capital GM over arrow square. That is acceleration to gravity on the earth is this. So I'll be having weight of the satellite in space is equals to M over 9 times G. So this now will give us, so the weight of the satellite in space will be mg over 9. Okay, and then I multiply. And also recall that this mg is the weight of the satellite on the earth's surface. So you say but weight of the satellite on the earth's surface is equals to what? Mg. So this equation now will change. Changes to say Ws now will be equals to We, that is weight on the earth's surface, divided by 9. And if I cross multiply, I'll have that We is equals to 9Ws. Okay, sorry, there's no need cross multiplying here. Okay, so what we are looking for is the weight of the satellite on space. So the weight of the satellite in space will be equals to 2000 divided by 9. Why? Because the weight of the satellite on the earth's surface is 2000. Okay, it's 2000. So you put the value there, 2000 as 2000 divided by 9, and I'll be having, so when I divide that, I'll have that the weight of the satellite in space is 222.22 Newton. Okay, so the weight of my satellite in space is 222.22 Newton, and this actually happens when the satellite is placed at a distance 2 arrow from the surface of the earth. When it is placed at a distance 2 arrow from the surface, this is the surface of the earth. From the surface of the earth, this is the center. That's the center of the earth. Okay, and I explained that the radius of the earth from its center, the radius is arrow. Now the distance of this satellite from the surface of the earth is 2 arrow. That means the total distance will be from here to here. That is arrow plus 2 arrow, which gave us 3 arrow. Okay, that gave us 3 arrow, and I raised this to the power of 2. That is 9 arrows square. Okay, and I separated them. I had m over 9 times capital GM over arrow square, and then you observe that this GM over arrow square is the acceleration to gravity on the earth's surface. So small g is this. So then the formula then changes to Ws equals to m over 9 times small g, and multiply it. The mass times acceleration to gravity on the earth's surface is similar to the weight of the object on the earth. Mg is similar to what? W. So the weight of the object on the earth is equals to mg. If I place it there, that means that Ws will be equals to We over 9. That is, the weight of the satellite in space will be equals to the weight of the satellite on Earth over 9. Okay, so the weight of the satellite on Earth is 2,000. So 2,000 divided by 9 gave me 222.22 Newton. So that is it in this case. Now let's look at the next one. The next one says, alright, in the next case we are told, that is for Roman figure 3. We are told that the satellite is at a distance equal to 4 times the radius capital arrow of the earth from the center of the earth. Okay, so we'll first project the diagram. This is the earth, and then we take a smaller sphere which will represent the satellite. Alright, so this is the center of the earth. This is the center of the earth. That's the center, and then this is the surface, isn't it? This point is the surface. Okay, now the radius of the earth will be from its center. This is the radius of the earth, this r. Okay, now they say the satellite is at a distance equal to 4 times the radius capital arrow of the earth from the center of the earth. This movement now is not from the surface but from the center. So from the center, I will take this, that is 4 arrow. So the distance of the satellite from the center of the earth, is 4 arrow. Okay, so it says from the center of the earth. So satellite from the center of the earth, its distance is 4 arrow. Okay, so we come back to that. Using Newton's law of universal gravitation, I have that the weight of the satellite in space will be equals to gravitational constant times the mass of satellite on the earth as mass of satellite on space divided by my distance now will be 4 arrow. 4 arrow, all raised to the power of 2. Okay, so take note of that. So that means this will be equals to capital GM small m over 4 raised to the power 2 is 16, and the arrow raised to the power 2 is arrow square. Okay, so when I separate them now, I'll have that the weight of the satellite in space will be equals to small m over 16 multiplied by capital G m over arrow square. Okay, it says but small g is equals to gm over arrow square. That is, acceleration to gravity on the earth's surface is capital G m over arrow square. So if I put it here now, if I place it here, I'll be having that the weight of the satellite in space is equals to m over 16 multiplied by small g. Okay, and this then we change to, say ws will be equals to mg over 16. Also recall that mg is what? Is the weight of the object on earth. Having this, that ws is what? Mg over 16. Now this mg is the weight of the object on earth. So it says but we is equals to mg. W is equals to mg. So that means that ws now changes to what? We over 16. Okay, and we is 2000. If you recall vividly, the weight of the object on the earth's surface is 2000. So divided by 16, 2000 divided by 16 will give us Okay, so this gives us 125 Newton. Alright, final answer, the weight of the object in space in this case is 125 Newton. So this one actually happens when the object is at a distance 4 arrow from the center of the earth. When it's at a distance 4 arrow from the center of the earth, we obtained the weight of that satellite. The weight of the satellite as 125 Newton. Okay. Alright, so in the next case, now it says, for each case in A above, derive an expression for the acceleration due to gravity gs in space with respect to the acceleration due to gravity ge on the earth. Okay, so we are going to establish a relationship between the acceleration due to gravity on space and then the acceleration to gravity of the satellite on the earth's surface. Okay, so in the first case, if you can recall vividly, the first case, recall that the weight of the satellite in space is the weight of the satellite on the earth's surface divided by 4. Okay, and now remember that weight, we know that weight is equals to mg, isn't it? Weight is equals to mg. So let's relate it here now. That means that we're having mgs equals to mge divided by 4. And that m we cancel out there, m. And so I'm left with gs equals to ge divided by 4. And we know, it says, but ge is equals to 9.8 meters per second square. That's the acceleration to gravity on the earth's surface is 9.8 meters per second square. If I put it here now, it means that the acceleration to gravity in space will be 9.8 divided by 4, which will give us that will give us 2.45 meters per second square. Okay, so the acceleration to gravity of that object in space is 2.45 meters per second square. However, the relationship between these two is this. So the relationship between the acceleration to gravity of the object in space and the acceleration to gravity of the object on the earth's surface is ge over 4. And this actually happens when the object was placed at a distance arrow from the center of from the surface of the earth. That was in the first case when it was placed at a distance arrow from the surface of the earth. So we are having that gs is what? Ge over 4. Now in the second case, you can recall that the satellite was placed at a distance 2 arrow from the surface of the earth, and we finally arrived at ws is equals to we over 9. If you can recall vividly, as for the second condition, then it then means that this will be mgs equals to mge divided by 9. And when I eliminate m, I'll be having that gs is equals to ge over 9. Okay, so in this case, this is the relationship. This is the relationship between the two of them is gs equals to ge over 9. So take notes in this case. And if you choose to find the acceleration into gravity, you just put this as 9.8 and you get the answer. Okay, so that is gs here will be acceleration to gravity of the planet on the surface, on acceleration to gravity of the planet in space will be 9.8 divided by 9, which gives you 1.0888. That is approximately, gs is approximately 1.09 meters per second square to 2 decimal places. Okay, then let's look at the next case. Okay, so in the third scenario, you can recall vividly that the ws is equals to we over 16. This actually happened when the satellite was placed a distance 4 arrow from the center of the earth. That is when we had something like this as the earth, and this as the satellite, and this is the center of the earth. The satellite was placed a distance 4 arrow. So when we solved, we finally arrived at this is the radius of the earth. Finally arrived at ws equals to we over 16. When we made use of this formula that was 4 all raised to the power of 2. So finally we arrived at this. Okay, but this happened when the satellite was placed a distance 4 from the center of the earth. Okay, so you come back here now. If that is the case, that means that WSCI is what? MGS equals to WE is MGE divided by 16, and M will eliminate M, and so you have what? GS equals to GE over 16. Okay, so that's the relationship between acceleration to gravity in space and acceleration to gravity on the earth's surface. In this case is this. So the acceleration to gravity in space is equal to GE over 16. That is, it is 1/16 that of the acceleration to gravity on the earth's surface in this case. So if you choose to impute the values, you have that GS will be equals to 9.8 divided by 16. That gives you 0.6125 meters per second square. You have that GS will be approximately 0.613 or 613 meters per second square. To 3 decimal places choose. The 2 decimal places would be 61. Okay, so we'll stop here for today. Thank you once again. This is Mathematics Made Easy. Please do not forget to like this video, subscribe for more educative videos. God bless you.